inglese, quindi anche per rispetto verso il nostro ospite d'onore di questa sera, da questo momento in poi si parlerà in inglese. So, ladies and gentlemen, it's an honor for me to welcome you here at the Green Week Festival of Sustainability. And first of all, I would like to welcome Professor Andre Gejm, and a round of applause for him. Thank you. It's kind of a tradition for our festival to present outstanding scientific research and innovation as part of our program, so we are extremely happy and honored to have Professor Gejm with us tonight. But before giving him the floor and before introducing Professor Gejm, I would like to invite here with me Davide Bollati, Chairman of Davines Group, who's supporting tonight and tonight's event. Grazie.
So we started this tradition of inviting and having conversation with Nobel Prizes last year. Last year we had, some of you remember, David Macmillan. It was Nobel Prize in chemistry. We learned on metallocatalysis, and it was a wonderful evening. I have good memories of it. And actually, David Macmillan told us that, according to him, in 10-15 years, this CO2 problem that we have that is causing global warming will be solved. It was quite after a couple of bottles of wine. Andre behaved very well at dinner tonight. He didn't drink almost anything. But yeah, we didn't have time. But last year, David said that in 10-15 years, we can solve the problem with the CO2 because we can transform CO2 in methanol with some chemical reactions. So we shouldn't worry about climate change much. In 10-15 years, it will take care of it. So now 1 year is past, so we still, we still have a few years ahead. But it gave us this hope. So this year we have Andre Gejm, and we will discover this special world of graphene. I think many of you don't know much about it. Andrea Pontremoli from della is an expert. In fact, he's in the first row to interact more. But so I'm very pleased to have Andre here. Thanks so much for joining, and looking forward to your presentation.
Thanks to Mr. Davide Bollati, and thanks to Davines Group. So, Professor Gejm, if you want to join us on the floor. I know that you personally don't like biographies or autobiographies. I read in your Nobel speech, but I want to give a few biographical details before giving you the floor. Professor Sir Andre Gejm is a Regius Professor and Royal Society Research Professor at the University of Manchester in the UK. He was awarded, among several awards, he was awarded the 2010 Nobel Prize in Physics for his groundbreaking work on graphene. He was born in Russia in 1958 to German parents, and he holds both British and Dutch citizenship. He began his academic career in Moscow. He then spent his postdoctoral research at the University of Nottingham, Bath and Copenhagen, and then moved to the Netherlands as associate professor before moving to Manchester in 2001. He has published many research papers, of which more than 20 are cited over 1,000 times, and 4 of them are cited over 10,000 times. 2 of the latter are now on the list of 10 of the 100 most cited research papers in human history. It's a funny fact. I asked him for permission about it, but he also was awarded the IG Nobel Prize in 2000 for his work on levitating frogs. And the IG Nobel Prize, as many of you may know, is a kind of alternative Nobel Prize, and is actually the sole winner in the history of the Nobel Academy to be awarded both the Nobel Prize and the IG Nobel Prize. So I am very honored to be with you tonight, and thank you again for accepting our invitation. Please.
Thank you very much. Yeah, thank you. Biographies are boring, so let's go to a little bit more fun, scientific fun. In the next 50 minutes or so, I'll try to be short and try to speak slowly, understanding that English not the mother language of most people, and please prepare questions if you want to ask at the end, Q&A time. So when someone gets a Nobel Prize or even a Nobel Prize, then people usually ask two questions. Okay, how did he get it, and why? Sometimes why this guy, why not me? So as I said, 50 minutes, I try to first to explain the story behind graphene and all the work we were doing, and then also try to explain why this particular material, not me, I'm just the bearer of the prize, the humanity awards itself, why this material deserves it. So the story behind, it's kind of proper probably to start with the time when I got my first tenured position. It was in the Netherlands, and when you tenured position and you can't be fired, you know, you can do some crazy things, even annoy your bosses, and instead of doing what people normally do what they promise in their grant applications. I was also had some lateral thoughts, what else can I do during my free time, saying late Friday nights. Those experiments later were called Friday night experiments, where you start doing something completely out of your main area of expertise, where you are just an amateur, complete amateur, and even could be considered as an idiot doing those things. In the Netherlands, in the place called Nijmegen, we get those magnets, which were actually ancient. They consumed a lot of electricity, a lot of cooling water, something like several thousand households consume simultaneously. So to put magnetic field, which was already 30 years ago, was not dramatic at all. So, but there was a pressure to do something from my bosses, to do something scientific with those magnets. And it's a lot of thinking, a lot of wasting time, and then a thought came along. What happens with water if you put in high magnetic fields? Those magnetic fields are approximately 10 times higher than, or even less than those you experience if you go to a hospital and use those MRI scans of your body. Not so great, 10 times maybe great, but reasonable by any standards. And water, what happens with water? Simple questions, but surprisingly no one before apparently asked this question. So once upon a time, on Friday night, as David told us, wine helps, but it was at that time, it was Belgian beer, so I opened a bottle of water and pour it inside the magnet. That's not what normal people do with an expensive scientific equipment. So Don't ask me why did I do this, but that was the story, and the result was spectacular. The water turned out not on the floor where everyone, including myself, would expect it. It ended up levitating. What you see here is about a tennis ball size of water floating freely in the air. It's a green laser shines it in order to see it better, and the water I forced it to move, pushing somewhere through the magnet. So I was educated in Russia, and as in Italy, it was good education at the university, so I realized immediately that it was not an anti-gravity machine. So the phenomena behind was diamagnetism. Most of people probably in this audience do not know what diamagnetism means. It's reaction of all atoms and molecules to external magnetic field. If you have a magnet and put against your finger, you would feel nothing, but in fact there is a small repulsive force between finger and any magnet. And apparently no one has thought, even people who worked professionally with high magnetic fields from their scientific cradle to their scientific coffin, thought that it would be enough, those magnetic fields 10 times higher than in hospitals would be enough to compensate the gravity. But gravity is also a relatively small force, speaking in physics terms. So it turns out to be okay. So I didn't think much about this experiment at all. Next morning I came back to the lab and told my colleagues that water levitates in our magnets. And people say, you must be joking. So I have to go back to show them. And then colleagues of colleagues start coming, and then other colleagues, and people in my society, they're very creative. So there were plenty of great scientific ideas what else can be put inside the magnets. So eventually everything was there and everything was levitating, except of course some substances like iron nails or nickel, which are ferromagnetic substances. 99% of matter around us can be levitated inside the magnet. So at a certain moment I got fed up and I decided to make an exclamation site. So I make this picture of a very small frog. It was 30 years ago and it was not very hard to do the frog. I'm condensed matter physicist and we usually deal with dead matter. And this was life science experiment which I only done in my life, and frogs, they jump, they stick to their fingers. It was very hard experiment. I admire life scientists who do all those experiments. So I have done also a small movie of levitating frog. It's barely alive, but you see it's still moving over there. So whether it was waste of time or not, from the benefit of 30 years later, I see that it's in dozens and dozens textbooks. And sometimes I go to scientific conference, several thousand people, and then someone in a corridor meets me and saying, "Oh, I know you." And I roll my eyes, "Not again, please," and etc. And then suddenly I see, "Don't worry, I have no idea what graphene is, but your frog." So, and I think it was a funny experiment. I got Ig Nobel Prize for this, agreed to accept it. It was possible to reject. But to rest my case, let me show a letter which I got from about 30 years ago, 25 years ago, from a girl from Alaska who writes, "I'm 9 years old and I want to become a scientist. I'm interested how you got the frog to float. It's very heartwarming letter, and I think it justifies all the time, not that much, and very little money I spent on doing this research. So when you learn doing something out of normal track, you start thinking all the time, what else is misplaced in this world? What else you can think about with help of the facilities and with help of expertise you had. So another experiment which came about 10 years later, 20 years ago, 2003 I believe, it's, I noticed from the literature that there is a very simple mechanism behind this amazing ability of geckos to climb glass ceilings and so on. And what shocked me, that mechanism behind is extremely primitive in physics terms. It's so-called van der Waals attraction. If you take your hair and try to stick to the surface, the hair sticks with the surface to the surface with a minute force, few nanonewtons. You won't really notice this stickiness. It's in semiconductor industry, I mentioned already today, if a dust falls on silicon wafer, it's impossible to remove this. On nanoscale, it's a very strong force. And you don't notice it with a single hair, but geckos learn how to grow billions of hairs on their toes. And those billions of hairs working in unison, and they at the same time attach to the surface, and nanonewton multiplied by billion times creates quite formidable force to stick them to any surface, even glass. So it doesn't involve any adhesion or adhesives, better to say it involves van der Waals adhesion only. So I thought, what a brilliant idea nature has done, and especially it's the standard size. I was working in my lab on my other projects which were paid by taxpayers and which I don't want to describe there because they are too scientific, like mesoscopic superconductivity and all other weird words you can learn from quantum mechanics. So I use facilities which I had to make small patches of those hairs which mimic gecko hair. As you see, they easily stick to each other. They also stick to the surface. My idea was I'll make a glove and let one of the students out of the window to show whether it sticks to the window or not. There was no lack of students, but there was a lack of material at that time, so I can manage to produce only about square centimeter of this material with quite expensively, I would say, and managed to make this small demonstration, a gecko toy, a Spider-Man sticking to there. It's very highly cited paper. It's very active area of research. People try to reproduce this, and they reproduced. I saw a man hanging from, a researcher hanging from the ceiling using gecko tape material. The problem is that it's gecko hairs, artificial hairs, starts and adhesion repeats only 1-2 times, 3 times maximum, and geckos somehow learn to clean up their hairs. We still, and researchers don't know how to do that. But this was my intervention into this very distant area from my research, and it was kind of successful, opening a new front. I have few more successes along the lines, and I don't want to describe those, and many more failures, I have to say. So let me come to the biggest success of my career, probably scientifically. after, or biggest after flying frog experiment, if I may. So the question was again very simple: how to thin graphite can be made. Graphite, very popular material. It's in any pencil trace. Scientifically, this material was studied for hundreds of years. It's known at least for 500 years. And colleagues and so on studied it extensively. And all I knew that it's very hard to make very thin films of graphite. And I was interested how to do that. Remember those Greek experiments? How Greeks came, Gedanken experiments, I have to say, mental experiments, thought experiments. They imagine take a stone and divide it into two, and then divide it into two, and two, and then they speculated that eventually you can't divide it anymore. And then they said, that's atom. That would be an atom. This is the name atom came from this Gedanken experiment. So I wanted to do something like that with graphite. Graphite is a very flaky material. I wanted it to divide and divide and divide. So it was a lot of effort. A PhD student spent 2 years without any success making thin graphite. And then one of a sudden, the idea came along from my postdoctoral researcher who was older than me at that time, and he said, you know, there are very thin flakes on graphite. This is what many researchers, hundreds of researchers, thousands of them, including myself, what we have done in studies of graphite, in studies of clean surfaces. You take Scotch tape, sellotape, to put it on the surface of graphite, and surfaces usually in air get contaminated. And then you pull this Scotch tape away and expose a very nice clean surface for minutes or maybe up to an hour. It remains clean. And all people studied this as brilliant surface. And because it's so atomically clean, you don't need ultra-high vacuum and other facilities to keep it clean. It's clean in air for some times. And everyone threw away this piece of tape, which is shown here. What people didn't realize before us that we're throwing this piece of tape into a rubbish bin, they possibly have thrown up their Nobel Prizes as well. So what we have done, took one of those sellotape pieces and look in the microscope carefully, rather than trying all those complicated scientific techniques my PhD student tried to do. And this is, it's dark because graphite is essentially a metal, and metals are not transparent. But then you start seeing very thin, transparent pieces. They're apparently thin because they are transparent. Some of those pieces are only a few atoms thick on this image. If you look carefully enough, there are pieces which are even thinner, and those pieces are graphene, and somehow no one noticed it before. So then the big question comes, why someone should be interested in some junk left on the sellotape? Education helps, and this is why I encourage everyone to go to the university if you can. Education helps, whatever way. So from the physics perspective, even from material science perspective, if you look at the world around us and everything what we have been dealing with. It has height, length, width. And this is why we called our world three-dimensional. There are three dimensions. We measure everything. You won't find materials which are, from perspective of material science, do not have height. And this material, graphene, has as little height as it's possible, only one atom, thick material essentially. Thickness goes as little as possible. Those materials, we call them two-dimensional materials because you can't make anything thinner than that. And people, 99.99%, except for those with strong benefit of hindsight, they always believe that those materials shouldn't exist in nature. And there are very powerful theorems which says they shouldn't exist. Because we live in three-dimensional world at finite temperature, room temperature, and in order to grow any material, you usually need to heat it up or do something to collect this material from atoms of molecules. And then there are vibrations in the third direction, and whatever you try to grow, instead of going into one-dimensional and two-dimensional thin wires or flat sheets, they eventually make three-dimensional architecture. You can just say the nature is smart enough, it wants to use all dimension available to grow all those materials. So how do we fool the nature in this case? In this case, you know, all materials contain rows of atoms and planes of atoms. And what essentially we have done, we extracted one atomic plane from already prepared three-dimensional material. It doesn't contradict to any of those theorems because, very simple, the material is grown at high temperature and our room temperature for some materials is low. You can't do it with every material. For example, you can't do it with gold, even when it's tens and hundreds of atoms thick. It would melt under our condition, but graphite does melt. It allows this trick to exist. And here is a picture how graphene looks like in real life. It's 1 millimeter size, and its contrast is enhanced by putting it on an appropriate wafer, so you can see it by naked eye. That's extracted from a bulk graphite, and of course you can use all the technologies available nowadays to look using electron beams to look how this material looks like. It's essentially a honeycomb of carbon atoms, which is cartooned on this picture. The next question comes, all right, you got those very thin materials which we were not aware before, so what? It's extremely simple, especially for a physicist. It's even simpler in terms of chemistry. It's only one type of atoms, and they are just in a very simple structure. And if it would be the end of the story, finding this material, how to make it, I wouldn't be sitting here. Then we started looking at this material and tried to look at its properties, and we found a lot of superlatives. It's of course the thinnest material. You can't imagine anything thinner than one atom. It's also stronger than, for example, diamonds. Of course, you need to take into account that it's one atom thick. It's stiffer than diamond, but at the same time, it's stretchable and pliable materials. It's like a little bit rubber. You can bend it and you can stretch it by 20%. It shows a lot of properties in for example, it sustains current, which much better than copper or silver or gold, completely impermeable. I might mention it later. And there are a lot of very boffin-like properties which I don't want to describe, but unfortunately I have to do to explain why the Nobel Prize was given. It was given actually not for graphene, it was given for elucidating properties of graphene. But over time, and from those all superlatives we learn, the biggest thing we learn that those materials like graphene, I mentioned more a bit later, which are only one atom or one molecule thick, they are very different from their parent materials, because usually you take a part of something and you believe that properties of this part will be just the same as the parent material. And it turns out completely untrue when you go to this fundamental limit. So the Nobel Prize was given for very spectacular behavior of electrons inside, essentially. And I'll give you a couple of examples how they are there. I'll have one scientific transparency, so fasten your seatbelts for a moment, and I'll write only a couple of formulas there. So we live in the world which moves at slow speeds relatively to the speed of light. And if you try to explain any material and any physics inside, from how computers work, how electrons move in any electronic devices, people usually use quantum mechanics and consider electrons as waves or as billiard balls moving there. However, there is a world usually studied by particle physicists or astrophysicists where particles matter is accelerated near to speed of light. In this case, there is another equation called Dirac equation, unlike in our world where we live by Schrödinger equation, and this is actually two basic equations with people like myself put a lot of terms at the end to explain physics, but those two basic equations describe our universe, or gives the best possible description for the moment. Where graphene comes into play, it turned out, due to this, its nature, how this hexagonal lattice of graphene, electrons behave not like massive particles, but they lose their mass in this equation. So particles in graphene, electrons in graphene becomes effectively massless, and then the behavior mimics what happens at ultra-relativistic speeds. So the message is that using graphene, you can probe in essentially tabletop experiments what happens in most powerful accelerators and neutron stars at a fraction of cost, and something which people can't probe at all. I'll give you one example, and this is called Klein tunneling. This phenomenon has been known for 70, 80 years. It's assumed to exist somewhere near the surface of black holes and neutron stars, but it doesn't happen in our world. So what Klein tunneling? Let me use only cartoons without any formulas. So if you buy a car and drive it into a wall, you know what happens. I don't need to explain further. If you live according to rules of this Schrödinger equation, which governs electrons and some atoms in our world and in semiconductors in your electronic circuits, we know that in this quantum world, a result depending on the height of the thickness of the wall, there is a phenomenon where part of the electron can go through and part will be stuck. That's phenomenon called quantum tunneling, used in many semiconductor circuits, for example. What Klein tunneling is, if you leave in quantum relativistic world and build up a car which would behave according to the rules which are followed by electrons in graphene, you try to build a barrier to localize those electrons around the car so the car can't go outside, and you can't do this. Your electrons, in our case, car behaving according to graphene's world, always goes perfectly outside this barrier. This phenomena is routine in graphene. It's explained, for example, why it's so conductive material despite being only one atom thick, because impurities or whatever you put on the surface of graphene, they are, due to this Klein tunneling, they do not affect conductivity as much as in any other material. There are many other examples of where nature of this mimicking of relativistic world comes in. It's the magic number, which is approximately 1 divided by 137. It governs a lot of phenomena which we don't, our universe wouldn't exist. There would be no oxygen, there would be no nitrogen, because all reaction which create heavier elements would be blocked. It's kind of, no one understands why this constant, what way it would be not so. We couldn't ask this question. There are this kind of philosophical problems. So where graphene comes from? About 15 years ago, we have done first experiment. Now it has become trivial, but previously at that time it was hard to make. So we look how graphene looks like. And here you see light goes through graphene. You can see that by naked eye what graphene is. It's a gray material, essentially. And the question which seems to be not important for a layman, but kind of scientific in a single layer. And this is what we measured. It's 2.3%. Sounds nothing, but then you write a few equations like physicists do, and you find out that this is pi times fine structure. As I told you, electrons behave like relativistic-like charges, and they are coupled constant between electrons and light. So you can see fine graphene. Okay, let me skip this example. It's David Bollati. I said that I can't say much about how graphene can be used for something green. Contributes to making our world a little bit cleaner and previous stuff. So people speculated into sheer gold. Is electronic waste, and we know that they all go into this rubbish bin easily. There is very much safer, not with mercury and not. So we put this electronic in an acid. Unfortunately, we get a solution. Paper covered with a lot from this goes through there, and you see solvent, and then it's not only gold is. We're working on this. We're continuous bringing some by the very small part of what this is not only one. In the graphene, this is boron nitride. 20 years ago, sisters and brothers under becoming kind of exciting those materials can bring. The question, one of those done, is to monolayer with, and then materials by or what a computer, and you can consider already put in this to make it artificial. Was my fact. 118 years we and many, if we do opposite, imagine what is left behind graphite if you extract the lab. This is the real space, It's so-called edge dislocation, how, for example, gases material using the technique by scotch tape, then again, but on a behaves not as is up, 3 dimensions, a new silicon edge of a lot of interesting asphalt in this of that graphical slide. You can make it include the and once which pin was millennium.
Andre Gejm, time, your turn. Perfect.
Sir, Andre, that
Yeah.
yes, Planck can be
Your hand so that we can bring.
Never meant that graphene physics, the real world.
Wondering why you.
About 10 years ago, somehow think that the first stone with your product, we now it's with patents, so it's costs a lot of money on doing.
The way you described your discovery, maybe move away from a specific project in mind, way to get it founded. But it looks like sometimes too, maybe you discover, maybe.
So, according to research these days on the in there, the style money comes, they start following unsuccessful. Do research on the with this way. Okay, you really deeper question is because 5-6 million your PhD to your postdoctoral, so you spend your time in failure. And somehow that's very badly because a lot of regions had this inkling to a few hundred years ago people were professional competition.
Da 2D a 3D, c'è un modo.
That's isn't this what back into some material sciences?
So, thank you. Was more or less in front of completely different phenomenon. So physical phenomena that are
materials and are completely different. Yeah, I tried also to the range of in the Y times it's conducting. Less react for material science didn't pass through the materials which was house about graphene. We accumulate application scientists.
I believe be used in
many. The first question you have asked. People look like that because word nana not. We use so many. The only it can injure you. Otherwise, in terms of health application for. Sure how much hype inside. So essentially of a structure of any shape which would part of your bone. People are looking at this one, but at the moment remark in condoms which you can buy than the normal one.
As you have said, so with this material.
In the industry in the future.
People are thinking etc. And people is burnt. It's burned warming than CO2. Now, burning this one, if you without oxygen, and it's pretty simple hydrogen people did companies, especially they want to specially use for valuable commercial to tarmac, graphene, and so there is a lot of potential to improve our
and lower than ever.
Opinion pieces. Reading, even I do think that the number of discoveries years ago when all those big sometimes then it was our life, the surface, each time with CO2 and solve those problems before.
Last question here from the first row.
Persona saranno praticamente ibride. Se questa è veramente nella storia del nostro.
Stating that artificial opinion, both will we be
have a drink about this, talk about artificial intelligence. There it's called sentient. It's not like even technology which combines those images, any text can be treated. Although if you make a sentence, so it's computer algorithms, but probably not on one of those people's pretty doing to ourselves.
In tonight's tonight, Grafene and of our Green Week Festival. Professor Gejm, siamo qua a disposizione.